Yes, ma'am. Good afternoon to one and all present here. I am Dr. M. Anand, Professor and Additional HOD of Department of CSE at Dr. MJ Education Research Institute, and I also serve as one of the coordinator of this faculty development program. It is my immense pleasure and privilege to extend a warm and cordial welcome to this distinguished gathering assembled for the inauguration of 6 days virtual faculty development program on transformative approaches in computing paradigm, machine intelligence, quantum computing, organized by Department of Computer Science and Engineering in association with the Center of Excellence in Computational Intelligence and Medical Technology and the Department of Cybersecurity, Dr. MJ Education Research Institute. To formally start this event, I now request Dr. S. Geeta, ma'am, Dean and Head of the Department CSE, to deliver the welcome address.
Thank you, sir.
Thank you, ma'am.
Good afternoon, one and all present here. Really, I'm happy to host the Department of Computer Science and Engineering in association with the Computational Intelligence and Medical Technology of Center of Excellence, and Department of Cyber Security is happy to host the 6 days FDP program in the title of Transformative Approach in Computing Paradigm, Machine Intelligence and Quantum Computing. First, really, I would like to welcome and thank our President Engineer ACS Arun Kumar sir, who is the pillar of support and always motivate us whatever the steps we have just taken it. Thank you, sir. And our mentor and our motivator, our Vice Chancellor, ma'am, Dr. S. Geeta Lashmi, ma'am. We welcome you, ma'am, on behalf of the department. Really, we are happy to have you as our Vice Chancellor. And you are motivating us in all the aspect of how to bring out the recent technologies into the curriculum, as well as to do such a kind of a program which will be useful for all the faculty members. Thank you for motivating us, and we welcome you for this 6-day FTP program, ma'am. We welcome you, ma'am. And I would like to welcome our registrar, C.B. Palanivel sir, Senior Additional Registrar, and our advisor, Dr. Mehta sir, who are all helping us to do such a kind of a program which will automatically inculcate us to bring out the hidden potential of faculty members to apply in recent technologies and developments, especially in the theme of quantum computing. Now people are trying to talk about more on quantum computing. Slightly we are deviating from AI to quantum computing. So we thought of thinking this 6 days program will cover both the machine intelligence and quantum computing, will help us to just carry out our research. So that is the intention behind it. And once we talk about this quantum computing and machine intelligence, I started to Google it. The first one, which I have just seen it, Dr. R. Murugan sir in NIT website. I just approached him by taking the number from NIT website, that professor's website. Immediately he accepted to give the talk on quantum computing with the image classification. Thank you, sir. Really, we are happy to have you on the first day session to deliver a talk on quantum computing in image classification. And I wish we will have we in the sense our department as well as the NIT, Murugan sir, to collaborate in bringing out the quantum technologies in different kind of forums. I'm expecting the same kind of help from you in future, sir. And I also welcome all the other 6-day speakers, which really help us to immediately accept our invitation. And we welcome you all. At last, our faculty coordinators team, and along with my co-convener, Dr. Dinesh Kumar, we are happy to welcome you, Dr. Anand, Mrs. Selvamina, and Menaha. We welcome you. And without the participant support, this would not be a big event. Really, I'm proud to say nearly 900 members have registered for it. So far, 350 members have started to just into Zoom mode now. We are expecting many more participants to join with us. Thank you, everyone. I wish this 6 days program will just bring knowledge of in quantum computing as well as machine intelligence to all of us. Thank you. Once again, I welcome the guest speaker of the day, our Murugan sir, as well as our Vice Chancellor, ma'am. Really, we're happy to have you all. Thank you. Selvamina?
Ma'am. Thank you, ma'am. It is my privilege to introduce Dr. Geeta Lashmi, ma'am, Vice Chancellor, Dr. MGR Educational and Research Institute, former Vice Chancellor, Tamil Nadu Government, the Dr. MGR Medical University, Hindi. Former Director of Medical Education, Government of Tamil Nadu. Former Dean of Stanley Medical College, Madras Medical College, Kilpass Medical College, Chennai. MBBS in Stalin Medical College in 1974 to 1979 in Madras University, and MD Madras Medical College in 1985, and PhD in Basic Science in 2007, the Tamil Nadu Dr. MGR Medical University. Is a Grand Doctor of Freedom Fighter, Tyagi Sidambaram Dandapani.
Doesn't matter.
Yes, ma'am.
So, thank you and for introducing us. But still, a lot is there. But I want, because I'm as a VP of this university, it's enough for me. And on behalf of the MGR Education Research Institute, deemed to be university with the accreditation of the Department of Computer Science and Engineering by the NBA and Abbott, with Dr. Geeta being the head of the department, taking care of the entire department on the scientific advancement and making the day-to-day advances practically into making it possible in the department, and also for training the faculty, training the students. I really appreciate her for taking this initiative each and every time whenever I see her. And on behalf of the management, we should thank our chairman, AC Shanmugam, and our president, ACS Arun Kumar, for giving this opportunity to come through the Zoom. And of course, this is a NAC A plus accredited institute going forward in going into the next goal. In this 6-day virtual faculty development program by the Computer Science and Engineering Department, which would be where we take forward the topic on the which is required in the days to come, the transformative approaches in computing paradigm shift with machine intelligence and quantum computing. In fact, all this will be into a day-to-day practice, which gives you the output in the advancement of the in this cyber world, on the space world, which we see every day happening, and which makes our life easy in the days to come. In fact, but it is all we, the human being, who has to work on it and make our life easy in the future, and so that it is accessible to everybody in an easy manner. So because that is how we want the future Indian citizen to go forward in itself. Though I cannot talk on more on this into, because I have to go into the depth of this knowledge. And though I know some part of this machine intelligence and quantum computing, I would like to also listen to the experts who are come from the EC department, NIT Puducherry, Dr. Murugan, who is going to elaborate and get into the way how we can go forward in changing the world through our knowledge, and transform into the practical way of making everything done through the scientific transformation. Thank you one and all for inviting me.
Thank you, ma'am. Thank you, ma'am.
Thank you, ma'am, for your inspiring words. I extend my respectful welcome to our distinguished guest, Dr. R. Murugan. Dr. R. Murugan sir is currently serving as an associate professor in the Department of Electronics and Communication Engineering at the National Institute of Technology, Puducherry. Prior to that, he was an assistant professor in the Department of Electronics and Communication Engineering at the National Level of Technology, Assam. He obtained his BE, ME in Embedded System Technologies and PhD from Anna University. Dr. Murugan has extensive academic and research experience in the areas of biomedical signal and image processing, medical imaging, retinal image analysis, computer vision, machine learning, and deep learning. He has published over 120 research papers in reputed journals and conferences, authored books under book chapters, and hold multiple patents to his credit. He has successfully guided several PhD scholars and actively contributes to the interdisciplinary research in AI-driven healthcare applications. His research focuses on developing intelligent computer-aided diagnostic system using advanced signal processing and deep learning technologies for medical image analysis. Dr. Murugan has also delivered numerous invited talks and technical lectures at the national and international forums. Thank you, sir.
Thank you, sir, for the nice introduction.
Thank you, sir.
Yeah, very good afternoon.
Yes, sir.
One and all present here. The today topic which is given to me is quantum computing for image classification. So, as is, if you look into this current research scenario, people are using many computational, algorithm, which include machine learning, deep learning, so many advancement of the deep learning. Now, the technology is looking into some other direction in various challenges which is faced in the deep learning. So that's why, like, people are want to use the another computing technology which is completely different from our traditional traditional computing mechanisms. Then we can utilize sometimes a dedicated quantum computing environment, or sometimes maybe combined with the traditional computer as well. So this topic is primarily will deliver into image classification. So many of the engineers, the technologists, which are primarily working in image classifications, maybe the image may be a conventional image, or sometimes it may be a medical image, or a satellite image, or any other image. So if any part, the image classification is the primary role of it. And the recent time, everybody is working with well developed deep learning or machine learning algorithms. So this lecture will give you some point of discussion how we can utilize quantum computing for classifying an image. So basically, this lecture I have been prepared from the basics. Since this is not a very advanced kind of talk, the main objective is that to make understand the audience the quantum computing in image processing. So in this way, if you look at the first discussions will be quantum computing for image classification. Okay, what is if you want use the quantum computing for image classification, we need to play with multiple technology. See, if you want to classify an image, only quantum computing will not help to classify an image in general. So we want to depend with the other other technology as well. So the primary is that, the quantum computing, which we are talking into this lecture. In addition to that, we require some other technology, like the artificial intelligence is one among them, then machine learning or any other thing which we can use. Then if you want to look it into the application perspective, suppose which we have a AI framework and we have an algorithmic framework, the quantum computing, and where this application is going to serve, which type of applications like which you want to use for it. So of course, if you select one is like a computer vision, since if you're talking about the image classification, it comes under the major category of computer vision. So the basic idea is that if you want to develop any image classification algorithm using quantum computing, so we'll all these three major framework that will be playing. Fine. So let's say for the which we are going to develop a quantum computing using image classification for quantum computing. Then what is the use of it? What is not there in the traditional mechanism, in the traditional algorithm? Why we want to go for the quantum computing? So it's a very straightforward answer is that to develop a faster, that is very, very important point here, and more efficient image classification system, right? So the word is very, very popular, faster. If you want to look it into the traditional AI or machine learning, deep learning, it is faster in some extent, but not all the ways, all the time. Again, it is depends on the input, what type of input which we are applying, and how much amount of input which we are feeding into the machine, and sometimes like how many how much infrastructure which we have. Infrastructure means the computing facility which we have, which all depends on the speed of the particular operation. Okay, so the second point is that more efficient. So the efficient word, it deals that even the traditional algorithm is also performing an image classification. But if you want to go with more efficient to the increased performance metrics, then the quantum computing is one of the major principle then we can utilize for the classification systems. All these type of the mechanisms which we are going to play with quantum principles. This is the another important point here which we need to discuss. Like if any quantum algorithm or any quantum computing algorithm which you are going to develop, so which we need to follow some certain principles of quantum, right? So this is the very generic, the overview of the image classification, and of course in the presence of quantum computing. Now maybe some of the audience like us may be very new to the quantum computing. They may heard about this word quantum computing in many places, but we need to thoroughly understand what is this quantum computing. See, a very simple word that we can understand is that quantum computing is the next generation computing paradigm, right? So what the traditional, the CPU or even GPU systems which we have, they're all the traditional computing paradigm. So now we want to migrate into the other generation of the computing paradigm, which is called quantum computing, right? What the basic principle are, which is behind, to develop this type of algorithm or the computing paradigm. Basically, there are multiple quantum principles which is available. One which we can call qubit, superposition, entanglement, and quantum gate. So these are all like primarily helping to develop the quantum computing. Okay, so here if you look at the first principle, qubit. So what is qubit? Like we know the bit, right? Generally, we can consider 0 is one bit or 1 is the another bit, right? And if you look at in this way, a classical bit which we sometimes will use either 0 or 1. But in a qubit can split in multiple stages or multi-state simultaneously. That means we can use 0, 1 at a time, or maybe we can use simultaneously. So both which we can use, that we used to call qubit. Apart from that, there are some other important principle which is also available or helpful to generate this type of computing paradigm, which include superposition, entanglement, quantum gate. So all these principle which we'll be looking into the further slides. So here I want to clearly explain what is quantum computing. Very simple. It's the next generation computing platform. Right. The next thing, which is also a very fundamental understanding for the audience, the difference between the classical and the quantum computing. So very, very straightforward answer. The classical computer is basically using the bits like zeros and ones and all that. And the quantum computing basically use zeros and one. So this will helpful, to calculate the billions of, the qubit in the cloud platform or in the cloud environment. And if you look at in the computing platform, either zeros and ones, it's assumed that whether it can be this or that, like either 0 or 1, or if you look at into the a typical switches or a transistors, which you can consider on and off. But if you want to both are on and off, if you look at, there is no, the boundary of it. That's why the quantum computing is basically helpful to foster this type of all operations. The next point of understanding is that maybe the continuation of the first slide, which we have been discussed. Why quantum computing for image classification? Yes, it's very, very important understanding for us. So traditionally, if you look at the classical deep learning algorithm, because in more than 25 years, the deep learning is actually ruling the research world or the technology. But now, what is the primary challenges in the deep learning? So first thing is that the deep learning require huge amount of data, which we have required. And when the amount of data is more, we required the huge computational facility, right? Computational facility which we required. And we both, the number of depends on the data. Of course, we require large computational power, and the particular data will occupy more memory space in the system, and also it will take long training time. Sometimes it may go for more than a week. This depends on the availability of the data. So to address all this type of the practical challenges, that we actually looking into the quantum computing. So what the quantum computing which we are going to perform, so it will accelerate the computation. So it means it will speed up the operations. And the second one is that it also helpful to improve optimization. Say for example, if you want to use any type of machine learning or deep learning, any of the neural network architecture, so we need to play many parameters, right? Which we used to call the hyperparameters of the neural network. So here what happened, the quantum computing is capable of, optimize all these parameters very fast, and at the same time, it will helpful to improve it. Then finally, if you look at if you want to handle high dimensional data, if you look at the 2-dimensional, 3-dimensional data, and the quantum computing based on the nature of the processor, it is capable of handling high dimensional data. So which all these like, which are helpful to quantum computing to make the classifications even better than the deep learning. Now coming into the fundamental about the quantum computing, like which we have been discussed in the second slide, there are multiple principles which is basically available in the quantum computing. Which one is to call actually, the first one is the qubit. Okay, so here the qubit is otherwise called as quantum bit. So generally it can represent 0, 1 or sometimes both simultaneously, which we can use. It's called actually qubit. This is the first fundamental principle in the quantum computing. And the second one is that superposition. Somewhere we learned the superposition principle, superposition theorem, right? So the same superposition principle, which is also applicable in quantum computing, because to handle a multiple state at a time, right? Say sometimes it comes into the zeros and ones, the combination. So we need to allow a parallel computation, okay, across different states. So here the superposition principle is primarily helpful to do such operation. And the third principle is that entanglement. This is also a very important principle, which is which when we are going to play a multiple states, then what happens is that the qubit become and correlated. Sometimes we need to exchange the information instantly or instantaneously. It means that what? Say, like we have a multiple state 0, 1, 0, 1, 0, 1. Like all these states which you need to process the informations instantly. So that like we can use this principle entanglement, or otherwise this mechanism is basically called as entanglement. Then the last one, the last principle is basically a quantum gate. Okay, if you look at in the quantum computer or any quantum mechanisms, the selection of the quantum gate is also one of the primary application, or we can the primary requirement to make it our operations effectively, or to make our operations very fast. So here, like that, we have a multiple number of n number of gate, like the quantum gate which we have. Hadamard is there, Pauli gate, CNOT gate, rotation gate. So all such type of gates are available. So these gates which generally to helpful our operations effectively, right? So apart from that, like a qubit, superposition, entanglement, and also the quantum gate, we have some other process also, like a quantum interference, quantum parallelism, like such type of principle which is also available. But these are all used for only some special case, like whenever we require. But the first four is generally will be predominantly used to develop any type of quantum algorithm. Now, coming into the another understanding about quantum algorithm in image classification workflow. Suppose if you look at any traditional deep learning algorithm, classical deep learning algorithm, how it will be, the performing by stage. Suppose we required an input image, and we required a typical deep learning or the convolutional neural network architecture. So the architecture itself, it is the capable of extracting the feature from the image, and after extracting the feature, then we can classify those images, right? So this is the traditional workflow generally which we need to follow. Suppose you have an input image data set which we have, and you need to develop a traditional CNN, then if you the CNN is capable of having a feature extraction, finally will get a trained network. So once the network has been trained, then we can test any image, then finally we can get a classification, either it is in A or B or whatever it is. But if you look at the same scenario into the quantum flow, so the image, the raw image, like which we need to do multiple steps or multiple algorithmic steps before into the classification. So what are those things? So this is the basic input. So from the input which we need to perform feature encoding, but in CNN which we need to do feature extraction, but in quantum which we need to do feature encoding. After feature encoding, we need to select the quantum circuit, then we need to measure the circuit, then based on that we can classify it. Okay, so for encoding the feature, like we have a different mechanisms, and also the selection of quantum circuit which we have been discussed in the last slide also. Then finally we need to perform the measurement. So this is the basic workflow of the quantum, how which we need to apply stage by stage for any type of classification. Okay, so now coming into the another understanding of the quantum is that QML. So the quantum algorithm is the common word which we know, but if you look at in the context of machine learning, right? Machine learning. So like we need to combine these two, right? Quantum with machine learning. So what we'll have to do, like what process, what steps which we'll need to combine to develop such a quantum machine learning algorithm. So generally the quantum ML combine quantum computing in one head and another head which we need to combine the deep learning. Then finally, like into select the appropriate parameter which you need to combine optimization algorithm also, right? So these three processes basically involved in the development of quantum machine learning. So in such kind of algorithm, we have a very popular approaches which is currently existing. One is called variational quantum circuits. Then another one is the quantum neural network. Then the next one is the hybrid quantum classical model. So all these models are like, basically, utilizing for different applications. Like maybe sometimes some approach may be helpful for some type of the applications, but some other one which will not perform it. So here what we need to do, we need to select an appropriate algorithm, then accordingly we can perform the classification. Like in the next slide, which we need to discuss, like before getting into the selection of the gate of a quantum, which need to perform the encoding technique. So once the image is ready, which the next step is to perform the encoding technique. So the encoding technique is primarily like, dealing with several mechanisms. One is called basis encoding, is a very popular one. This basis encoding primarily helpful to convert the image pixels into the binary quantum state. So this is the most primary and foremost process that we need to do it in the quantum computing, and especially in encoding. The next is the amplitude encoding. So here what we need to do, we need to store some information, okay, in terms of qubit. Then we can depend on this encoding mechanism. And we want to do some kind of rotation, right? We have a data, then we need to rotate it. Then what happens, the encoded data can also rotate with the qubit with the help of angle encoding. So depends on the process, we can have to select these encoding mechanisms accordingly. Then the encoding mechanisms will perform. The next we can go for selection of the gate. So here coming into the discussion of the selection of gate, or we need to depends on there are three fundamental mechanisms again. So which one among is the quantum neural network? Okay, so here how we can define this QNN, or like Very simple. The QNN, the quantum neural network, is very similar to the classical neural network. So the classical neural network, what we have an input layer, we have an hidden layer, then we have an output layer. Very in a simple way of understanding of the classical neural network. In the same way, if you look at the QNN, what happens is that which you need to have a quantum gate, and also we need to have a parameterized quantum circuits, then finally which you need to do the quantum measurement. So these three, which is basically involved in the QNN, I mean quantum neural network. So what way this quantum gate or the circuits or the measurement which will be helpful in the quantum, it means that it will helpful for the faster operation, then of course the parallelism, then also it will helpful for the reduced feature dimensions. So all these aspects, so primarily the QNN is helpful. So if you want to select the QNN is one of among the process, then of course which we can address all these type of challenges. The one algorithm which is called QNN, like quantum neural network. The other one which we can call it as hybrid quantum classical model. This is also a other quantum model which is very popular in many applications. So here, what is the change which we are doing in here instead of in the traditional our neural network? It's very simple. Here, the word which is hybrid, it means that which are doing two process. One way is conventionally and other process is quantum based. So in that way, what happens is that the feature extraction, which you primarily dealing with the classical CNN, and then the quantum layer, which will primarily we are using for the classification. Okay, both which are involving. That's why it is hybrid. So for example, if you use CNN quantum layer, then finally if you use a softmax function, you will get a classification. So this type of model, which is called hybrid quantum classical model. Then this model is also a very popular QCNN, quantum convolutional neural network. This is also a very popular model, and most of the researchers are, which are utilizing this QCNN model. So what is this, the QCNN model, how it will be looking like? It's very simple. How we, in the CNN, how we actually dealing with convolutional layer, the same way which have a quantum convolutional layer here. And the second is which we are polling layer, quantum polling, then finally a quantum feature extraction. So here in each and every steps and layer which we need to perform the quantum principle. That's why it is called quantum convolution layer, quantum polling, quantum feature extraction, and so on. Like these are all very popular, the quantum networks, like which is currently existing and also utilizing for many applications, we can say. Okay, so while understanding all these fundamental principles of quantum, so how a pictorial way of understanding this framework? Say if you look at the CNN, very simple. If it is an image, we need to perform a convolution, and we can use the polling layer and activation functions all, and finally the fully connected layer, which will be helpful for classifying the image what you are applying. The same way, if you are utilizing for the quantum, the QCNN, what happens is that, so which you are primarily utilizing the quantum computing, like for hitting a feature or extracting the feature information. Then finally, we can use the classical computing for the classification stage. So here in the quantum, the feature extraction stage, which we need to use the quantum encoding and quantum convolutional layer, then finally measurement. Then based on the measurement, we'll get the cost function or any of the weight update. Then finally, we'll get an output. So this, the pictorial information will give you a complete overview of how we can differentiate these two in image classification. Okay, so as of now, we have discussed from starting what is quantum computing, how the quantum computing is actually different from the classical computing, and in the quantum computing, like what are the basic principle involved, what is the process involved, right? Then what are the different types of quantum algorithm which is available. So we have discussed up to this whole fundamental informations, which will be primarily required as the prerequisites for the audience. Now, if you look at this quantum mechanism or a quantum computing, in this way, either it can be a traditional quantum computing, or it may be a hybrid one, or it may be QCNN. So all these type of we can utilize for image classification in many applications, So here I have been highlighted some of the applications in medical imaging. Why? The reason is that, so I am basically working with my research group with medical images. So that is why we actually use quantum computing for medical image classification. So here, if you look at in this context, so there are different applications which we can, if you're working with some cancer images, we can use cancer detections and classification. And if you have, the fundus images, the retinal disease classifications, if any of the retinal disease like diabetic retinopathy, glaucoma, and many diseases, we can use quantum computing for an effective classification. And also we can use to extend this type of problem in brain computer diagnosis, skin lesions, then even COVID-19 analysis or the classification also. Like we have so many, the wide applications in medical imaging. So here what, the some of the into applications, so how we effectively use this quantum algorithm for image classification. So recently we have been actively working with retinal disease classifications. So in the coming discussions, we'll see how the quantum computing is performing well in retinal disease classification. Okay. Look at this slide. It's a very interesting slide. Yeah. So as I said, the retinal diseases. If you look at in this context, the retinal have a multiple disease. Retina is having many diseases like diabetic retinopathy. We may heard about glaucoma, cataract, so many diseases, AMD, which we have been heard about it. This disease is very dangerous disease. Recently, it is affected for many Indians, which is called retinal detachment, the name of the disease. So what is this disease is that, say for example, suppose if you are going to sleep in the night, right? Maybe if you look at, if you wake up in the morning, what happened, maybe your image may be blur, or the half of your image may be, vision may be blur. We can't able to, identify what type of disease it is. So this type of disease actually we used to call retinal detachment. That means that the retina generally located on backside of the eye, in the outermost membrane of the eye. What happened? The retina may be detached from their original position. Due to this detachment, what happened? You see the half of the vision you can't able to see. The same impact we can see in the image also. This is the retinal fundus image, which is acquired from the ophthalmoscope, right? So you can see the vision is also blurred with the normal vision. If you have a normal vision, you can able to see the complete vision. And if it is detached one, half of the portion you can see here, it is it is blurred. Right? This is the impact of this disease. So what happened? So this disease is one of the very even challenging disease for the ophthalmologist. So that the motivation factor which we have actually working for classification of retinal detachment. Now, if you have a question, why we have a multiple diseases, many diseases of eye diseases, and why we need to select for the retinal detachment? The answer for this type of question is that if you look at these images, it will be the answer may be very clearly justified. If you look at the first image, this image, so this is basically a normal image. Okay. So in this image, there is no abnormal symptoms which is present. If you look at, and if you look at the second image, what happened due to the effect of detachment, there are swelling is inside, right? And the same way, you can see here, the other stage of retinal detachment is that the whole part of the retina, which is actually some portion of the retina is actually relocated. And sometimes what happens, you can see here, the multiple portions are relocated. So it's not clearly able to see so many patches actually created in the retinal image. So this type of diseases, like the feature of this retinal detachment disease, it is very hard to classify which type of retinal detachment disease. So we required a trained and experienced ophthalmologist to classify such diseases. So that's why which we have been motivated to classify or to develop such classification algorithm for this retinal detachment. So the takeaway point from this slide is that the retinal detachment is fundamentally classified into three types. One is rhomotoneous retinal detachment. This is the early stage of retinal detachment. Then tractional retinal detachment. Then exudative retinal detachment. So these three types of retinal detachments are very, very challenging to classify one another. That's why we required a strong algorithm which will be primarily helpful to classify such stages. Right. So again, very fundamental understanding about the retinal detachment. So the detachment means that it may cause the permanent blind loss. Sometimes we can't be able to recover the vision. So even the retinal detachment, the early diagnosis is also very, very challenging. And sometimes, so for this type of challenges, we require automated AI tools. And this development of this AI tool, the quantum machine learning is actually offering an efficient computation. So that's why we have actually utilized the QML for retinal detachment classification. So the statement of the problem is very, very simple. Like classical CNN model required large data. But if you look at the retinal detachment case, we do not have such huge amount of data, like 50,000, 70,000, 1 lakh. We do not have any type of retinal detachment data set. At the same time, based on the dimensionality of the image, we have a high computational complexity and the need efficient medical image classification. Then of course it will need to improve an early RD diagnosis. If you are finding the detachment in early stages, then it is very easy to treat by the doctor. So in that way, we can save the patient or a person vision. So these are all the statement of this problem which we have been carried out. So now coming into for this type of work, we have utilized the quantum machine learning. So this quantum machine learning, as I said, maybe in the previous discussion also, it is combined both AI and quantum computing. Then also it is used quantum circuits, and it supports for efficient feature representation. Then finally, we are using a hybrid quantum classical learning. So all these utilizing these steps. So the contribution of the work is that we have recently proposed. So this particular model is introduce a quantum model, and of course, for performing the pre-processing, we can use for the quantum encoding. And finally, we are comparing with the quantum CNN with the classical convolutional neural network. And finally, the reduced model complexity with an very good accuracy. So all this, what we are theoretically understand from the quantum computing, which we actually contributing towards this retinal and detachment classification. So this is the fundamental methodology which have been utilized for retinal detachment classification using QCNN. Here the methodology is going like this. This is the data set. So the data set which have been collected from many hospitals in and around India. Then we have developed our own data set. The name of the data set, which is called retinal detachment data set. Retinal detachment data set, which is publicly available in IEEE Dataport. You can just type IEEE in IEEE Dataport retinal detachment data set. You will find the data set, which have been launched by our research group. And so this data set, which we need to classify with the quantum algorithm, we have multiple steps. The first one is that we have preparing the data preparations. Since the amount of data which have been collected, it is very, very limited, so that we need to perform some type of augmentation. Then simultaneously, we have done some type of pre-processing mechanism, resizing, grayscale, then normalization, all these things which you have done. Then after that, once the data is normalized, then which you are ready, then the next step is that actually which we need to, going for the feature extraction. So here the quantum circuit, the selection and quantum convolution that we have performed here. So here what happens is that the normalized image, which have been divided into different qubit. One is 4 qubit, 8 qubit. And depends on the qubit, we have selected the patches, 2x2, 4x4 patches. Then we have performed the quantum encoding. You know what is encoding. Then also we have done RY encoding. Then we have selected randomly. Then finally, we have measured the parameters in poly-Z principle. Then finally, we'll get a feature map, output feature map. So once the feature map is ready, the feature is ready, we are using a CNN model for the extraction followed by the classification. Then finally we'll get the training and the evaluation metrics. Right. This is the fundamental workflow that we have been utilized for this retinal detachment classification. So whatever we have explained in the methodological diagram. So here I have been written in the word input image, pre-processing, quantum encoding, and finally it will go for the convolutional layer. So here coming into this way, so the data set and pre-processing. So primarily we have a data set, and this data set is divided into 3 major categories along with the normal image, right? So the normal which are mentioned is the healthy, exudative, homogeneous, and fractional images. Then the image normalization and augmentations that we have been done. Then we have done the efficient pre-processing mechanism. So for experimenting this methodology, we have utilized 1,600 retinal images. So this 1,600 images out of 4 classes. Then finally, we have trained 1,200 images in this the architecture, trained, then 400 images which are used for the testing. So as I said, in the pre-processing, we have done 32 cross 332 resizing mechanism, then grayscale conversion, then normal traditional normalization techniques, then finally test and train and spec test. Then once the pre-processing has been done, that we'll go for the quantum layer, the second way of process. So which we based on the qubit, the 2 cross 2 patches that we have done, then RO encoding, attachment, all these principal mechanism we have done. Then finally polyset principle helpful to measure all these parameters. Then the training setup which have been utilized in the algorithm is that we have used an Adam optimizer, 30 number of epoch, patch size 4, then loss function is cross entropy. So these are all the hyperparameters that we have been utilized to train this network. So here, the whole workflow, like what we have been explained, I think it's very clear to you, like what the data set which you have been organizing, like what architecture which you have done, and what type, what are the hyperparameters which is we primarily utilized for this in this work. Simultaneously, like all this, the quantum basics of the quantum mechanisms, we have a certain mathematical framework which we are dealing. So for example, how we are doing the normalization process, how we are doing the attachment. Now all this we have mathematically which we need to define. So here actually in the particular slide actually I have been given the mathematical framework, but all these things are very easy to understand. Say for example, in a classical computing, how we are representing zeros and ones, the same way how in a quantum bit, how we are representing zeros and ones, right? The same way, if you look at in the other way of understanding the normalization principle, alpha square beta square equal to 1, like so many like the mathematical framework which is involved in this. So this I'm not going to very deep into this mathematical framework. It will take some time, but rather it is very easy to read. I will supply the PPT to the organizer. So you will get the PPT, then finally later you can read how actually the framework is actually modeled. Okay, what theoretical, the understanding or principle which you are explaining. So here the mathematically also actually represented. Okay. So now we have a data set and also we have a model. So we have trained. So the remaining case, like we have actually tested those images, right? Once the network is trained, which you need to test. So for testing, like we have done so many data analytics, right? So the data analytics basically involving to prove efficient of our model. So in that way, what we have been done initially, like before developing the QCNN model, we have done the same data set with the traditional CNN baseline model. So if you look at the baseline model, the average is the accuracy is very minimum, right? Only 90% which have been achieved. And of course, in medical image classification, 90% is not an optimum result. So then what have been done, we have also done a hybrid QCNN model for the same data set. If you look at the 3%.
Sir, sorry, sir, your presentation is not visible. Can you please check it out?
Sir, is it visible now?
Yes, sir. Visible only, sir.
Okay, okay.
Yeah, please proceed, sir. Thank you.
Thank you, thank you. So if you look at in this way, like the same data set which have been used for hybrid QCNN model, so there is a 3% of improvement, like from 90 to 93. So in medical image classification, so the improvement of 3% is also a very, very challenging task here. Then what happens is that if you also analyze this data, like how if you want to do some data augmentation, then we have analyzed whether there is the possibility of an improvement. That also actually then we have done. So we just augment the data. Then still we have the further scope to implement the result. Then we have very limited data also, but still it will not be further improved. Then what happens is that then which we have been using, we also analyzed the the augmented model with the quantum model what we have been developed, but still 1% of improvement that we have been achieved from 93 to 94% which we have been achieved. So that is an improvement again with the help of the data augmentation. Well, so all these analysis, what we have been done, these are all the background data analytics that we have been done. Since the challenge is that there are twofold. One is that we have a quantum compute. We have a quantum algorithm which we have developed. But this quantum algorithm which we are running into a classical computer, right? So that is a big challenge, right? But still, if you look at the quantum algorithm which we are running into the classical computer, which we are getting 94% of an accuracy in the classification. Then what happened? So there is another way, like how to improve the result from 94 to further. That is the another, the challenge that which are coming in our mind. So here, the answer is that if you run this quantum algorithm in a quantum computer, then of course it will be a ultimate options. You will get an efficient metrics, which we can say efficient classification metric. But still in this, the research has to be progressed in what way which we can improve this type of results. In that way, we have done a lot of data analytics. And the data analytics which we also done with different quantum simulator, because with our own the limitations, purchasing a quantum computer is actually very costly, right? So we also done this type of analytics with the quantum simulator. This type of simulator which is available, you can also do this type of things. So the name of the simulator which we have, Pennyland, Circu, QSIT, and QLAC. So many, the quantum simulators which are available. Sometimes some companies are providing some limited options or the limited version of the simulators, and some are actually providing on finance basis, payment basis. So to improve further in this results, so what we have been done, so we have used this type of simulator also, and which we are using this type of simulator, like we have been started from the scratch, and we have also done so many data analytics which we can discuss one by one, so that you will also get more insights into how we can do this type of analysis for your work also. So we have been initially used circuit simulator. So if you look at this simulator, the training test is same and the number of epoch 25. Here actually we have used 8 qubit. Okay, and if you look at the 8 qubit, and of course the simulation time is also, very decent. And if you look at the metric, it's not very optimum. It's very, very less when you are going to use the QPT8. Then we have thought of, selecting a QPT 4. Just look at QPT 4. What happens is that we are getting complete, 100% accuracy in this. There is no, even it is not in one image, it's also negative. So, you can see the simulation time is also very decent, just 443 seconds, which you're getting the whole data. So the same simulator, which you can use, if you're using in the traditional computer, and which are not getting more than 94. And if you're using for the corresponding quantum circuit simulator, the results are very good. This is the advantage of the quantum computing. The same way, we have also tried with the Qiskit simulator, and you can see here the number of qubit is 8, and the quantum time is also more. And even if you look at the percentage of accuracy is also very, very less. The same way, when you are reducing the qubit, you can see here the time is also very decent, and you can see the complete, the successful accuracy, and even there is no 1% of the deviation also. This type of analysis, which is also we have done. And the another way of understanding is that data analytics is that we have tested with other simulator, QLAC, and you can see for the 8 qubit we have selected, still even not 60%. And if we are selecting the 4 qubit, we are getting in 100% accuracy. So in all the analysis, what we have been done, when the number of qubit is less, which we are getting very good result. The number of qubits are more, actually the time is also taking more, and maybe some other reasons which we are not getting an optimum result. That is what actually we have analyzed from these, 3 different type of simulator experimentation, right? So the result is that when we are dealing with the conventional computer with this quantum algorithm, 95% only which you are getting, but when you are going for the traditional CNN, it's only 94. So we have some improvement in this. So when you are going to use the the quantum computer, quantum simulator, which you are getting from 94% into the 100% of possibility of an accuracy, that is possible only because of from the quantum computer. Okay. So that way, in terms of performance analysis, we are getting very competitive accuracy with the fewer parameter, and also efficient classification performance, reduced time complexity, as you can see in the screen chart. Then also we have been much more better than the traditional CNN. Traditional CNN, which are giving only 94%, right? So that way the metric is also very, very good, and the comparison also we have been done. Then the advantage of this quantum machine learning is that, so there is the efficient image feature representation, then potential speed up, quantum speed up, and lower parameter, and it will be scalable for medical AI systems. So all these put together, to get a better classification in this retinal detachment. Yes, well, coming into the challenges of this, many challenges, of course. We have only the developing country, India, like us, we have a very, very limited quantum hardware. Still, we are not converting, to migrating to a traditional computer into the quantum computer. That is a challenge. And suppose sometimes you have a quantum noise and image encoding complexity whenever you are going to use the encoding mechanism that we have. And limited qubit availability. So for example, if you want to use these type of simulator very, very limited quality. I mean, the qubits availability is available, and it is very costly also if you want to take a license or a payment basis. Then the conclusion is that, like the quantum machine learning, which are providing a promising result in medical image classifications. Of course, if you use a hybrid QCNN, that is also helpful for improving the efficiency. So this, I mean, very, very useful in retinal detachment diagnosis. At the same time, we can use for some other medical image classification also. So on the whole, which will have a fruitful and future potential of healthcare AI with this quantum technology. So the future work, maybe if you are an audience today, maybe tomorrow you can use this type of idea for your own work. So you can also explore some advanced QCNN architectures. Then here we have used only one disease, retinal detachment. You can use multi-class retinal detachment. There are multiple diseases which you can put it into the data set. You can classify multi-class data. That is also a very good research problem. Then we are doing the simulations here. You can also do some real-time clinical deployment. We can also use some, the explainable quantum AI. We have explainable AI, but explainable quantum AI is also developing in another the technology. We can also use explainable quantum AI so that we can get more lesions understanding how the retinal detachment is actually the lesions are differentiating from one stage into another stage. So that way also we can get clear lesion-based explainability. So that may be also a kind of future works. So yeah, still which we are working quantum computing with many medical imaging problem, but still there are a lot of scope and the limitations which are not obtaining an appropriate result. So our research group day night, which we are working to get some more good results. Maybe in some other the forum or venue, I can share some more good problems with good result. Since this research is very, very hard to do, but still which we are trying to attempt this problem. So this today have been given very limited results which have been recently obtained. So thank you one and all for providing this such an excellent opportunity. And if you want to collaborate with us, or if you want to do any type of, if you want to do postdoc or any PhD, or if you want to do any internships, we are very happy to welcoming you all. So you can just simply write in a mail. So we'll happy to collaborate with you in future also. Thank you so much. If any queries, maybe I'm happy to answer.
Thanks a lot, sir. Insightful and engaging section on quantum computing for image classification. Your presentation has laid a strong foundation for the rest of the program. Thank you, sir, for your valuable time and the contribution. If you have any queries, please post in the chat box. Dear participants, if you have any queries,
Keep on posting this feedback only.
feedback from only, sir.
Yeah. So no issue if you have no questions in this time. Maybe if some other time, if you are coming anything, you can just feel free to write. We are always open. We'll answer your queries.
Thank you, sir.
Yeah. Thank you. Thank you,
okay.
Geeta ma'am, for inviting me and the opportunity to share my thoughts.
Wind up the section, sir.
Thank you. Sure, ma'am.
Okay. Thank you, sir.